In this video, I'd like to talk a little bit about the third experiment we're going to be doing, which is the quantitative analysis of household chemicals. So this experiment is going to be the first experiment where we're going to do some chemical reactions. Unlike in experiment 2, where we did all physical processes, this experiment is going to involve our first chemical reaction. So to distinguish, we remember that physical processes or physical reactions, they involve the transformation of matter from one state to another, but it doesn't involve changing its chemical properties. When we change the chemical properties, that means that we start with some material, and when we're done with our chemical reaction, we have a new material that's made up of a new combination of atoms, or a different number of atoms than we started with. Now, there's another couple of important words that we have to determine also, and this is the difference between qualitative versus quantitative analysis. So another thing that distinguishes experiment 2 from experiment 3 is the fact that in experiment 2 we were concerned with the quantitative nature of the experiment, meaning we were concerned with determining how much of something was present. So we took measurements and we used significant figures to come up with percent compositions for the different materials that were in our mixture. In this experiment, we're not concerned with how much of something is in our mixture, but what is in our mixture, meaning we're going to use chemical reactions to identify a substance and its chemical properties. So where is this important in the real world? Well, one of the areas that it's really important is in crime scene investigation. I'm sure you guys have seen the show CSI or other shows that are similar to it. And this happens frequently. You'll get some kind of unknown at a crime scene. That could be gunshot residue. It could be some kind of unknown material that you don't know what it is, or a fiber. And then you have to do some kind of qualitative analysis or quantitative analysis to figure out what is in it and how much. So crime scene investigation is one example. And another really important example of qualitative analysis is when you're doing a cleanup of a site, for example. So if, for example, a company has a chemical spill, or you come upon, you discover that a site that was formerly owned by some company, they were dumping toxic chemicals, you have to know, in order to clean it up, what chemicals were dumped and in what quantity. So qualitative analysis is really important for a variety of reasons. Okay, so in this experiment, I want to point out a few things before we get started. First and most foremost, it's going to be a little interesting to do some of these experiments because normally you would actually physically do these chemical reactions in class. Now, some of the reactions you're actually going to be able to do at home so that you can observe them at home as you would in lab. They're going to be simple reactions that involve household chemicals that are completely safe. And you're going to be able to observe those chemical reactions at home. Now, for the ones that involve chemicals that are a little too hazardous for us to send you, what we're going to do is we're going to allow you to observe those, but we're going to allow you to observe them digitally. Meaning we're going to set the experiment up and show you a video of the experiment taking place, and you're going to be able to see all of the important observations that you would in lab, just like you were standing there at the bench. So what should we be observing? We should be looking for things like color changes, gas formations, the odor of gases. Now, I'm going to have to tell you if there's an odor. Temperature changes. Again, you can't feel the reaction vessel, but so I will tell you if there's an apparent temperature change. And you must note all of these on the data sheet. So as you're going through this video, I recommend that you have your data sheet out and that you start to write your observations down in pencil on your data sheet or on a separate piece of paper, and then collate that onto the data sheet. And as always, when we're doing lab, anytime you write a reaction, it must be balanced and it must have phase labels. So even if there's a partially completed reaction in the book that you just have to finish off, you still have to balance it and you still have to write phase labels. This is very important. So in essence, you've been warned that for all the labs to come, that reactions must be balanced and have phase labels. Now, some of the reactions in this are actually very simple and straightforward and done with very, very safe chemicals. However, some are done with some more toxic chemicals. One of the chemicals that we use in this experiment is concentrated sulfuric acid, or H2SO4. This is an extremely caustic chemical and would cause burns to eyes and skin. So if we were in lab and you were to do this experiment, we would have to wear safety goggles at all times and make sure that our lab coats were closed. if you ever get sulfuric acid on your skin in future experiments, you're going to want to make sure that you go over to a sink and rinse it with tap water and let your instructor know, because if you rinse it with tap water quickly, it will wash away and it won't hurt you. Or it'll hurt you much less than if you were to just let it sit on your finger and say, oh, I'm not going to worry about that. It'll be okay. Now, some of the reactions that we are going to do and observe must be done in a hood, and this is because they generate toxic gases. So I will mention to you the reactions, and in particular, it's the iodide reactions. Those would be done in a hood because of the toxic gases. And then when you're using the Bunsen burner like we did in the last experiment, you must use caution, keeping your hair away from the Bunsen burner and keeping any loose articles of clothing or paper away from the Bunsen burner. Okay, so let's kind of get started with the household ammonia part. So the first thing I want to do is I want to introduce you to something called litmus paper. Litmus paper is basically a specially treated paper. It comes in two different forms, blue and red. And what it does is that treatment is designed to tell you if there's an acid or a base present. So red litmus paper, if you test it with an acid, nothing will happen. If you test it with a base, the litmus paper will turn from red to blue. So you'll see up here, this area was the untreated area. This is an area that was exposed to base, and you get this blue coloration. With blue litmus paper, it's treated to detect acids. So with blue litmus paper, it will turn red when it's exposed to an acid, and it will do nothing when it's exposed to a base. So blue litmus paper will turn red in this area where the acid was exposed. Now, let's look at the properties of liquid ammonia. So ammonia is an example of a weak base. That's something that you should know going forward, that ammonia is an example of a weak base. So one of the things that you're going to observe is what happens to dry and to litmus paper when you hold it over ammonia. So if ammonia is a base and liquid ammonia evaporates, making ammonia gas, we're going to want to use red litmus paper to detect the presence of ammonia. So if you were to hold this red litmus paper over just a regular old solution of ammonia, the ammonia would turn the litmus paper blue because it's a base. We're going to see this in more detail when we test for ammonia gas in just a second. So now let's talk about the difference between dry and wet litmus paper. Now, normally you always make the litmus paper wet before you use it. The reason for this is because wet litmus paper will allow whatever is in the air or in the liquid to react with the litmus paper more efficiently. So for example, if we make ammonia gas, the gas itself is neither an acid or a base. So the ammonia gas is neither really an acid or a base. It has to be put into water so that it can form either hydronium, H3O+, or has to form OH- hydroxide, and then that is what makes it an acid or a base. It needs that water to be around. So when you put the dry litmus paper over it, it does change a little bit. You'll see a little slight tinge of blue, but it's not very significant, and that's because all that's on that litmus paper is a little bit of moisture just from the atmosphere. Not much, there's a little bit, because there's always some water in the atmosphere. But if you wet the litmus paper and you put a good amount of water on it, now that ammonia can react with the water and become a base. So you're going to notice that when you use wet litmus paper, it's going to work much more quickly and give a much better response than with dry. So that's how we use litmus paper to detect acids and bases. We want to make sure that the litmus paper is either wet or we put it in a solution that has water. Now, let's look at the thing that we're going to be more interested in. So the thing that we're going to be more interested in is the properties of the ammonium ion. So we're going to detect the ammonium ion by looking to see if we can make ammonia gas. So the reason why we have the liquid ammonia here is to understand that when we make ammonia gas, we can detect its presence using the litmus paper. If we were to put red litmus paper around something that makes ammonia gas, we will see that red litmus paper will turn blue because ammonia gas is a base. So when it comes to the ammonium ions do something special when you put them in the presence of sodium hydroxide. And let's actually take a look at what happens when we do that. So in this experiment, we're going to kind of fast forward a little bit here. Oh, no. So we're going to take some ammonium chloride, which is this compound right here, and now we're going to do our experiment. So we're going to add some base to it, some sodium hydroxide, and we're going to form a solution. So we're going to add the ammonium chloride and the sodium hydroxide together. And we're going to form a solution where those two are allowed to react. Now, in this video, they heat it a little bit. You actually don't need to heat it. The reaction is vigorous enough that you can get a good litmus paper response without heating it. So the heating it is not in our experiment. But in this case, they heat it just to make the reaction go a little faster. Now, if you notice, let's just go back for a second. You'll see what they did was they took the litmus paper and they wet it. And now they're going to put that litmus paper over the reaction, and it's going to turn a bright blue. So what that tells us, that bright blue that formed, that tells us that there was a gas above that reaction. Over this reaction was a gas, right? He didn't put the litmus paper, if you watch, he or she does not put the litmus paper into the liquid. They just put it in that air that's above. So we must have made a gas in this reaction. And the way that this works is we're doing an acid-base reaction. So ammonium chloride is the conjugate acid of ammonia, meaning that it is the acid form of ammonia. And when you add a base to it, like sodium hydroxide, we do a metathesis reaction where we pull a hydrogen off of the NH4+, and we make ammonia gas. So one way to detect if something makes ammonia gas is by adding hydroxide, and then it will form ammonia gas. And we can detect this ammonia gas by looking at the wet red litmus, which turns blue. So you can see if we do the net ionic reaction here, where we take away the spectator ions. The spectator ions are the chloride and the sodium. Those just remain as sodium chloride in solution. You'll see that the proton, the H+, gets transferred to the OH-, and we make the NH3 gas. So one way to detect if we have ammonia is by adding a base, which will react with the ammonium ion to make ammonia. So using these types of sort of qualitative analysis, we can do the same thing and see if smelling salt, for example, has ammonium in it. Now, smelling salt is this compound, ammonium carbonate. And ammonium carbonate spontaneously decomposes. So you'll notice that this reaction is an interesting reaction because we only have one reactant and it breaks down into multiple different products. This is an example of a decomposition reaction because we start with one thing and break it down into multiple things. And it turns out that this breaks down and produces the ammonium produces ammonia gas during this decomposition reaction. So what would you expect the blue litmus paper, what would you expect the red litmus paper to do when you were to hold it over the ammonium carbonate, the smelling salts? What you would see is you would see the red litmus paper turn blue because we're making ammonia gas. So that's what happens here. And you'll notice that this is an interesting thing because ammonium is an acid and carbonate is a base. So in essence, the reason why this decomposes is because we have an acid and a base that's put together into a singular compound. That's why we don't have to add an external base because we have a base already attached to the ammonium. Okay, so this is what your data sheet for the household ammonia looks like. We observed the effect of ammonia on, we didn't observe the effect of ammonia on dry and moist litmus, but I explained to you what would happen. So on dry litmus, you would see a very slow, gradual reaction because there's a lack of water. Whereas with the moist litmus, we would see a rapid change to blue because we know that moist litmus has the water on it to allow the ammonia to become a base. Now, if you were to hold, this is something to think about. If you were to hold the ammonium chloride, which is an acid in solution, if you were to hold the blue litmus paper over an acid, should it change color? Well, it will not, right? Because the blue litmus paper, the red litmus paper is only sensitive to bases. So the ammonium chloride needs to be transformed into ammonia gas in order for it to change the red litmus paper. So the effect of ammonium chloride on litmus paper there would be no effect because this is an acid, the acid form, not the base form. And then we saw the most important one that we observed was the effect of ammonium chloride plus NaOH. Now, in this case, we saw that it did turn the litmus paper blue, suggesting that it had the ammonia gas formed. The smelling salts, we're going to look at the additional observations now for the fertilizer and the smelling salts. So you take a small amount of fertilizer, a white solid, and you add a few drops of NaOH. You hold the moist red litmus paper over the reaction and it turns blue. So based on that result, does fertilizer contain ammonium? So you're either going to select yes or no, and then explain what the observation indicates. So the no should be here. It's just missing from the data sheet or from the scan. But you're either going to select yes or no depending on that observation. The same thing goes for holding the moist litmus paper over the smelling salts. So when you hold it over the smelling salts, the litmus paper turns blue. So does the smelling salts contain ammonium? And here you're going to write your observation turns the litmus paper blue, and whether or not you believe that the smelling salts contain ammonium. Okay, so the ammonia was sort of a separate part of this experiment. Now, for the next 4 anions, the reason for that is because ammonium is a cation. So we are looking at testing it as a cation. For the second part of this experiment, we're going to look at 4 different anions. Remember, anions have a negative charge. So there are going to be 2 tests for every anion. There's going to be an initial test where we add concentrated sulfuric acid to a sample containing one of the ions, and we're going to get a unique observation depending on the ion. So in table 1, it gives a list of all the observations. We're going to see these in the next few slides, but I'm just showing you here that for the initial test, there is a table that gives you a nice, concise explanation of what should happen when you have these ions present. Once we do our initial test, we add the sulfuric acid, we're going to get an idea of which one is present. So if we were to see violet vapors of I2 formed, if we were to see the reaction form violet vapors, that would probably send us in the direction of thinking, well, we have I-. But we have to also do a secondary test to really make sure that we have that in the solution. So we do a secondary test called a confirmatory test. And each ion has its own confirmatory test. So you need to know this for the quiz. You need to know what the initial test result should be, and what confirmatory test you would have to do for each ion, and what the result should be. And we're going to see each one of these in turn. But I sort of summarize everything on this slide to make it easier for you to have in your mind as we go through. So now let's look at the reactions of carbonate. And carbonate is actually one of the ones that you can do at home. So you can test a few different substances for carbonate using an acid, but instead of using sulfuric acid or hydrochloric acid, which are very strong and dangerous, you can use a simple at-home acid like vinegar. Vinegar is a weak acid that will work just fine, will make these reactions take place, and is something that is completely harmless to use at home. So you can use vinegar to test certain chemicals at home to see if they have carbonate. We'll talk a little bit more about that in a separate video where we do the at-home part of this experiment. So let's look at the initial test first. So with every one of these ions, so for example with baking soda, which has the carbonate in it, we're going to do the initial test first. So when we add the sulfuric acid to the sodium hydrogen carbonate, that's this compound. Sodium hydrogen carbonate is a carbonate, CO3 2- that has one H+ attached to it. So we call that sodium hydrogen carbonate. That's the active compound in baking soda. So now let's take a look at what happens when we add a strong acid to sodium hydrogen carbonate. And in this case, you'll notice that this is called a double displacement reaction. We're going to see those in more detail next time. And another thing is in this reaction, they're going to use hydrochloric acid. We would normally use sulfuric acid, so it doesn't really matter which acid you use. You're going to get the same result. So now if you observe the reaction, they added the acid. We see that there's vigorous bubbling. So we're making a gas. That bubbling, that that happens is the indication that we're making a gas. And the gas that's formed has no color. We don't see any particular color in these bubbles. It's not green or yellow. So this is an indication that we've made a colorless gas. Now, if you were to hold your nose over this gas, and you can actually try this at home with baking soda and vinegar, you should not smell anything from the gas itself. If you use vinegar, you may get a slight vinegar odor, but you shouldn't get any other odors than just the vinegar itself. Another thing that you would notice is that the reaction would be warm to the touch. So let's look at this reaction, and we're actually going to talk more about this in more detail about this reaction in the next experiment. But when you react sodium hydrogen carbonate with sulfuric acid or any other acid, you make three products. You make carbon dioxide, which is the gas that's formed. This is the colorless, odorless gas that's formed. We make water as another product, and we make the salt of the sulfate and the counter ion that's over here. So what's actually happening is we're doing a double displacement reaction where we take the hydrogens and we put them onto this base that is the hydrogen carbonate base. And we make something called carbonic acid, which has a chemical formula of H2CO3. And what we're going to learn in the next experiment is that H2CO3 decomposes spontaneously and rapidly into carbon dioxide and water. That's why we form carbon dioxide and water. Now let's take a look at the confirmatory test. So if you were to add sulfuric acid to your sample of an unknown, and you were to get a vigorous bubbling with a colorless, odorless gas, that would be an indication that you had carbon dioxide. One thing you'll notice is that carbon dioxide is neither an acid or a base. So if we were to hold either red or blue litmus over this reaction, we would not see any change to that litmus paper because carbon dioxide is neither an acid or a base. So that's another indication, because there's going to be another experiment where we will hold litmus paper over it and we will get a change. So you get bubbling, a colorless, odorless gas, it's warm to the touch, and litmus is not affected by it. Now let's look at the confirmatory test. So in the presence of carbon dioxide, we can hold a drop of barium hydroxide over our reaction, and we're going to get a new reaction. This carbon dioxide is going to react with the barium hydroxide to make barium carbonate solid. So what's going to happen is the presence of CO2 and barium hydroxide. So if you have barium hydroxide liquid, aqueous, in the presence of CO2 gas, that drop is going to start to turn cloudy and form a white precipitate. So let's actually see that happen. So in this experiment, what we're going to do is we're going to do our metathesis reaction where we're going to take some of our carbonate and we're going to put that in a test tube. And then we're going to add some of our acid to it. So again, we're going to see our rapid bubble formation with the carbon dioxide formation and the clear gas. And now what they're going to do is they're going to allow that gas to go across and go into a solution of barium hydroxide. So in this solution, we have barium hydroxide. And you'll notice that as the carbon dioxide bubbles into that solution of barium hydroxide, the barium hydroxide turns white, indicating the presence of barium carbonate that's formed, the barium carbonate solid. So this confirmatory test where we have the barium hydroxide and we either hold it over the carbon dioxide source or we bubble it through, is going to make barium carbonate solid. And you can actually run this exact same reaction with calcium hydroxide. It does the same thing, barium or calcium hydroxide, but in our experiment we use barium hydroxide. So you can actually try at home using some vinegar to determine if the following contain carbonate. Now I have to say, do not try to add vinegar to anything else besides the following three. These three will result in a completely safe product. If you were to add vinegar to something that is not one of these three, you risk having a not so great reaction. So we're only going to use the following three in our try at home: chalk, table salt, and baking powder. So now that we know what the reaction should produce, if we form a colorless, odorless gas, we should be able to detect whether one of these has carbonate whether any one of these has carbonate in it or more than one. So we're going to have a separate video that talks about how to do those experiments at home. Now, another thing that's really interesting to do is to try to detect CO2 in your breath. So if you were to take some barium hydroxide, a little drop of it, and suspend it and breathe on it, and take a nice breath and breathe out onto that barium hydroxide, it's going to turn that barium hydroxide cloudy because a product of respiration of our metabolism is carbon dioxide. So when you breathe out, that carbon dioxide can be detected by the barium hydroxide drop. So now let's look at the data sheet. Baking soda and sulfuric acid we observed. You can write that down. Baking soda and vinegar you can leave off of this data sheet. We're going to try that one at home. And then also the chalk and the chalk you're going to leave off. All we have to do is write down number 7. You're going to write your observations for number 7. And that's it for the data sheet for this experiment. The rest we can try at home on a separate data sheet. Okay, now let's look at sodium chloride. So here's the initial test. We're going to add H2SO4. So let's take a look at what happens when we add H2SO4 to sodium chloride. Okay, so we're going to skip forward a little bit. Now, what we have here is we have, we're going to start adding some things. Okay, yeah, so inside of here, he's put the sodium chloride. This is regular old household sodium chloride solid. And he's put it into a test tube, just like we would in lab. And now on top, what he's going to do is he's going to have a pipette that has H2SO4 in it. Now, in this particular experiment, what he's going to do that's a little different from what we would do is he's going to hook up a little hose that he's going to put into a separate thing of water. And then he's going to use a pH meter to detect a change in pH. We actually would just, instead of taking a hose, we would just use a piece of litmus paper over this to detect whether it turns acid or base. But this is actually a more sophisticated way of measuring the effect of the gas and see whether it's an acid or a base. So let's see what happens. And you'll notice he has his safety glasses and his gloves on because these are corrosive chemicals that will be formed. Okay, so now he's going to inject that sulfuric acid. I think he's going to talk about it for a little while longer. We can probably skip ahead. Here we go. Okay. So now we just added it. Now what we're going to observe is we're going to observe a reaction between it where we form, we're going to have bubbling. So this looks kind of similar to what we saw with the carbonate, except this gas has a little bit of a pungent smell to it. Now, if you were to just waft a little bit of that gas in our lab, you would notice that it would have kind of a strong, pungent smell. It's a little difficult to explain, but it would be similar to smelling like a bleachy, like a Clorox bleach type cleaning agent. That's what it would smell like. Now, what's happening is the gas that was produced is going through this tube and is going into the water. And this thing right here is a pH meter. And a pH meter tells us how acid or base how much acid or base there is in the solution. So you'll notice that the number was a 2. And that tells us normally neutral water has a pH of 7. When the pH goes below 7, that tells us that an acid was formed. So if we were to have held red litmus paper over this, we would get, if we were to have held blue litmus paper over this, we would get a strong, intense change in that wet blue litmus paper to red. That's because the gas that's formed is hydrochloric acid. So when we run this reaction, we take sodium chloride and H2SO4. What happens is the protons from the H2SO4, the H+, go over and react with the NaCl and make HCl gas. And that comes off as a gas. When this gas interacts with the blue litmus paper that's a little bit wet, it becomes an acid and turns that blue litmus paper red. And the other product that we get is the sodium sulfate. So that's our initial test. What you would see is you would see bubbling of a colorless gas with a pungent odor. That's HCl. And this gas, because it's an acid, will turn wet blue litmus paper red. Now, what if we were to do a confirmatory test? So what if we wanted to see how can we make sure that that sample, that unknown, actually is in fact sodium chloride and not a carbonate, if we weren't sure. So the confirmatory test for this is going to involve dissolving the sample in some water, adding a little bit of nitric acid to acidify, and then adding silver nitrate. And let's look at what happens when we do that. So what we did in this video is we took a little bit of our unknown, our NaCl, and we put it in here. It's a white powder, and then we added some water and we made that white powder dissolve. So now we have our NaCl in water that's nice and dissolved, and we're going to add some silver nitrate. And let's see what happens when we add the silver nitrate. When we add the silver nitrate, we get this nice white precipitate that forms. So now let's take a look at what's happening chemically. Well, what's happening here is we're getting a, so if the unknown has the presence of chloride, it forms a white precipitate of silver chloride. So this is an example of a metathesis reaction, where we're exchanging partners and the silver is going with the chloride and the sodium is going with the nitrate. And we know from our solubility rules that silver chloride is a solid. It will not dissolve in water. It's a white solid. And the sodium nitrate is just a spectator compound, and that stays in solution and does nothing. So if we had chloride in this unknown, we're going to get a nice white solid when we add silver nitrate. Now, one point that I want to make is, why do we have to add nitric acid to acidify? The reason for this is because water itself is not just always pure water. A little bit of carbon dioxide can dissolve into water to form carbonate, the same carbonate that we had in the previous reaction. And carbonate, if carbonate is around from just the carbon dioxide that dissolves in water, that will also form a precipitate with silver called silver carbonate. So we have to make sure that we get rid of any carbon dioxide in water. And the way that we do that is we add acid. Now, if we go back to our previous slide, when we add acid, that's going to get rid of any carbonate that's dissolved and turn it into CO2 gas, and it goes away. So the reason why in this step we add a little bit of acid, that all that is to just get rid of any dissolved carbon dioxide that's in there. That's why we put the 2 drops of the nitric acid. So whenever we're doing these tests with the silver nitrate, we put the acid in just to make sure we get rid of any carbon dioxide that's in the water. Now there's another thing that we can do to test for the presence of sodium ions, and that's a flame test. So when you take a little bit of sodium chloride and you put it in a Bunsen burner flame, you get this nice bright yellow flame that you would see here. So the flame test for sodium ion, that's another thing we would do in lab. And you would just take a little bit of the sodium chloride, put it onto a little piece of wire. They call it nichrome wire. It's an alloy. You take a little bit, put it on, and you put it in the flame, and you get this nice yellow flame. So now let's look at the data sheet. So the effect of H2SO4 on table salt, we observed that in the first video. And here you have to write a balanced reaction for that process. So you can put that down on your data sheet. We also observed in the second video that when we add silver nitrate on a table salt solution, that this effect of silver nitrate, we saw in the video what that does, that makes that precipitate. Now, this is an interesting question. In all of these experiments, we use our source of water, we use a special type of water called distilled water. Actually, in our lab, we use a water that's even better than distilled water. We use water that has been deionized. So why do we use distilled water? The reason for that is because distilled water or deionized water has all of the ions that are already taken out. So there's nothing in the water that could potentially cause a problem. Now here's why, so that you can write that down for why we use distilled water. It's because it's purified and has no ions. Now here's why we actually do that. If you were to just take some regular old tap water and add silver nitrate to it, this is what that solution would look like. And notice that the silver nitrate has caused this little discoloration to occur. When we form a white discoloration in the solution, that is an indication that we have made a solid, a white solid. So does this result here, when you put silver nitrate into regular old tap water, does this indicate that there are chloride ions in that regular old tap water? So you should be able to tell me from this result whether yes or no are there ions in that tap water. And that relates to why we're using distilled water. It prevents us from getting a false positive from anything that's interfering in solution. And then we saw what happens when we put the salt in the flame. You can write down your observation for that. Okay, now let's look at the reaction of sulfate. So now sulfate is a major component of Epsom salts. Epsom salts is a compound of sulfate that is magnesium sulfate with some extra water in it. These waters are called waters of hydration, and you'll see that in Chapter 1 and Chapter 2. Now, the initial test, we're going to add our sulfuric acid like we normally would, like we did in the last two. And in this case, we don't even need to put a video because the sulfate here is the same as the sulfate over here. So we have sulfate plus sulfate, and it does nothing. When you have two of the same things, basically you don't get a reaction because the sulfate and the sulfate are the same. There's no reason for it to do anything. So we get no significant reaction. You may feel it turn a little bit warm, and that's because these waters of hydration will react with the acid a little bit. But oftentimes students actually don't even feel it turn warm. So what I would say is if you were to add H2SO4 to something that was an unknown and you were to get no significant reaction, that would probably mean that the unknown is a sulfate because they're the same things. So now let's say that we did get no reaction and we wanted to make sure that we had sulfate in our sample. What test can we do? What confirmatory test can we do to check and make sure that it's actually sulfate? So what we can do is we can take our unknown, which would be a white powder. We can dissolve it in water just like we did with the sodium chloride. Add a little bit of nitric acid to it, again, to get rid of any carbonate that's in the solution. And then we can add barium chloride. And here's what will happen when we do that. So down here is our dissolved unknown containing the sulfate. And we're going to come in with some barium chloride. Just a few seconds. And there you go. So when that barium chloride gets added, it's going to make a nice white solid. So when we have magnesium sulfate in solution and we add barium chloride to that, the double displacement reaction or the metathesis reaction is going to result in the barium going with the sulfate and the magnesium going with the chloride. From solubility rules, we know that barium sulfate is insoluble in water and it's going to make a white solid. So the magnesium chloride, on the other hand, is soluble, and those are just going to be spectator ions. So the flow in this case is if we see no significant reaction in the initial test, then in the confirmatory test, we're going to try barium chloride, and if we get the white solid, we have confirmed the presence of barium sulfate. So on your data sheet, you can write the effect of H2SO4 on Epsom salt. I described that in the initial test. And then you can write the effect of barium chloride on the dissolved Epsom salt. So you saw that in the video here. Now, the reactions of iodide, I should say. These reactions must be done in the hood because some of them will make toxic gases. So now let's look at the first one. In your book, this is a bit different. This is not following that standard protocol. We're going to do the standard protocol of the initial test and the confirmatory test in just a minute. But we're going to look at some other reactions of sodium iodide with some other compounds. So one reaction of sodium iodide and bleach is an interesting one and is one that we're going to watch. So let's take a look at and see what happens when we add bleach. Now bleach is the common name for sodium hypochlorite. Okay, so you should be able to use nomenclature to see what that is. Okay, so what happens is you get a sort of an orangey brown solution, and what you would notice is in this reaction you'd get a very unpleasant odor that comes off, which is probably hydrogen salt, which is probably a compound of iodide that has a strong odor. So that's why we do this in the hood. But you get this sort of reddish coloration to the solution when you add sodium iodide and sodium hypochlorite. Now, one of the products that you form in this, and this is what has this reddish color in water, is iodine. Elemental iodine, I2, in water. And we can actually do a separation. So you'll notice in the procedure of the experiment that you can use mineral oil or hexane. These compounds are non-polar solvents. So water down here is a polar solvent, and mineral oil and hexanes are non-polar solvents, and they separate. So this is like putting oil and water together. They don't form a mixture. So we're going to see what happens when we put a little bit of a non-polar solvent in the presence of that solution that we just made, and see what happens. So in this video, they're going to do the reaction first, and we'll just take a look and see what happens. So here they have their iodide dissolved in water. And then now they're adding in their bleach, which is going to make our brownish color. So we've made iodine. And then see here, this is the hexane, or the mineral oil. You can use either one. And that mineral oil or hexane forms a layer on top and separates from the water phase, or the aqueous phase. Then over time, we get this separation, and some of the color here goes into solution up here. And we get this nice pink layer above the solution where the molecular iodine, I2, has gone a little bit into the nonpolar layer. Now, if you think about it, I2 is not a very polar compound. It's a nonpolar compound. So it makes sense that some of that I2 is going to go into the nonpolar phase, or the nonpolar solvent. Okay, now let's go back to our standard sets of reactions where we're going to do our initial test. So this is going to be the sodium iodide and sulfuric acid. Now you'll notice on the procedure that this is done somewhat backwards, but we're going to do it in the right direction for the digital experiment. So we're going to do our confirmatory test where we add the sulfuric. We're going to do our initial test where we add the sulfuric acid, and then we're going to observe what happens. So let's take a look at that. Okay, so in this case, they're putting some potassium iodide into the, they're putting some potassium iodide in, and then they're going to add the sulfuric acid. Now, you'll notice that this one is the concentrated sulfuric acid. In the first experiment that they did, so let me just go back a little bit. Okay, so in the first experiment they do, just so that you guys were all on the same page, this one is dilute sulfuric acid. So when you do dilute sulfuric acid, essentially nothing happens, or very little happens. The compound kind of dissolves, but you don't get a reaction. Now, concentrated sulfuric acid is important. We use concentrated sulfuric acid because it's much more reactive. Now, what you see here is you form this sort of dark purple solution, and if you look carefully above, we can go back a little bit, and we'll get it where it just started to react. You'll notice that if you look right here, there is a sort of a purple haze that's over the solid. It is a little hard to see, and you might be able to see it better in the first couple of seconds. Yeah, you can start to see the purple kind of coming off, and there you can kind of see a little puff of purple up in the top. That little bit of purple that's coming off, that purple color is the violet vapors of I2 that you're getting, and I2 has a purple color. Also, you're going to get a very nasty smelling rotten egg smell from this that's formed. There's a gas that's formed. And in this case, this is one of the reactions in this experiment where you actually don't have to know the reaction because it's complicated. you make a variety of different products. You make I2, which is that purple-violet gas. You make H2S gas, which has a rotten egg smell. You make HI gas, which also has a rotten egg smell, among other products. So in this case, you just have to know that if you were to add sulfuric acid inside the hood, you would see violet vapors of I2 and a foul-smelling gas would be formed. And that would be an indication that you had reacted this, that your unknown had the iodide in it, of the sodium iodide. Now let's look at the confirmatory test. So again, we're going to use silver nitrate to see if we can form a precipitate. So let's take a look what happens when we dissolve some potassium iodide in water. Oops, let's go back just a second. Okay. Okay, so in the initial, before we added our reagent, we had a solution. Now, this solution is not perfect because they didn't allow their sodium iodide to dissolve fully. So you can see that it's not fully dissolved. In our lab, we would allow this to fully dissolve, and it would be a nice, transparent, clear solution. But when they add the silver nitrate, and you're going to see that right now, you form a yellow precipitate. This yellow, off-white, sort of bone-colored, yellowish precipitate. And that yellow off-white precipitate is silver iodide. So we can confirm the presence of iodide if we see in the initial test this violet vapors and foul-smelling gas. We can then dissolve some of our unknown in water, add a little bit of acid to get rid of the carbon dioxide and the carbonate in the water, and then we add our silver nitrate, and we're going to get silver iodide. And again, this is a metathesis reaction where the silver reacts with the iodine and the sodium moves over to the Na, and we get silver iodide solid. Because of our solubility rules, we know that this is insoluble. And then we get aqueous NaNO3, which is spectator ions. And this solid has a yellowish color. So if we get an off-white precipitate from the in the product of this confirmatory test, that's an indication that we have iodide and not chloride, because chloride would be white. Okay, so now let's look at the data sheet. So the first one is the reaction of bleach with sodium iodide. You can write your observations there, and make sure that you include the observation of what happens with the mineral oil. So you're going to want to write your observation of the initial reaction, and then sort of you can separate it or put a little line and then say this is what happens when we add mineral oil. Now you'll notice that 19 and 20 are backwards. The first thing we did was we looked at the effect of H2SO4 on NaI. So the video where we form the violet vapors, that's going to go here in this set of lines. And then the confirmatory test is actually 19. So you're going to write your observations for the confirmatory test there. Okay, so now for the unknown, what we would do is in lab, and this is kind of the fun part, because you're going to now take some white solid that you don't know what it is, and you're going to take all the information we just did, and then you're going to actually do it. You're going to actually go in and figure out what was there. So this is sort of your CSI moment. So we have to first do our initial test. We're going to take that unknown, we're going to put a little bit in a test tube, a couple of spatulas full, and then we're going to add our H2SO4, because in every single anion, so the possible anions are either carbonate, chloride, sulfate, or iodide, right? Those are the four that we had the initial and the confirmatories. So then we're going to use that table to see which of the possible gases it could possibly be. Which of the possible, when we add the H2SO4, not gas, I shouldn't say gas, which of those four compounds it is based on what happens with the reaction with H2SO4. So now let's look at our observations. So we take our solid, put it in the test tube, add a few drops of H2SO4, and here's what we get. The solid results in the evolution of a gas with a pungent odor. The gas has no effect on moist red litmus paper, and it turns moist blue litmus paper red. So now, if we look at our data in the table, we're going to write down we're sort of going to think about those observations, and then we're going to decide on what confirmatory test to do. So based on these, we're probably going to be thinking about chloride as our unknown, because the big giveaway is that it turns the moist litmus paper red. So we're forming an acid, and the only one that forms an acid for a gas is chloride. So now we're going to perform the confirmatory test for your suspected ion. following the directions. And then if it's consistent with the ion, then you have the ion present. So what we're going to do is we're going to dissolve the white solid in water, and we're going to add a little bit of acid. I didn't write that here, but we add a little bit of nitric acid, and then we add silver nitrate, and a white precipitate forms. So based on these results, you're going to write down your unknown ion. You're going to write down your observations for both tests in line 22. And then you're going to say, these results suggest that I have this because of this and this, meaning my initial test showed this, my confirmatory test showed this, these are consistent with this ion. I'm going to submit my report to the judge. The person is either guilty or not based on this verdict. So that's this experiment, and you basically saw all the reactions now. So what you have to now start to think about is, if I were to get a mixture of some of these unknowns, how could I detect what's in it, and what reactions would I get depending on what I had? Okay, guys. So this will be due on the date that the syllabus says it's due. And if you have any questions, you can contact your section instructor regarding the contents of this video.